technology series, and this is our engineering blog where we meet interesting people who define what's going on in the back end, who do interesting technologies which we also use, and technology of interest to new kind of startups which are growing in Soma and elsewhere. And today our guest is Marius Eriksen. Marius is a lead engineer at Twitter. He is the creator of Finnegan, which is the networking layer Twitter uses for all kinds of services. He is a Scala expert. He is the author of Effective Scala guidelines, which are used by beginning and experienced Scala programmers everywhere for their organizations. He is currently the co-chair of Commercial User of Functional Programming Conference, which will be in Boston, September 22nd to 24th. So in his GitHub is full of yummy repositories. So basically, he's an all-around functional programming guy, and he's originally from Norway. And we are basically going to talk about the technologies he develops and Twitter uses, and some lessons from it for all kinds of companies which want to scale and basically reach this amazing level of scalability what Twitter is right now. So let me just ask you first a little bit about your background, because we know your engineering side, but so you're originally from Norway.
That's right. Yeah.
What is it about Scandinavia which makes so many good programmers, and actually programmers with a functional twist to come out of that? Like a lot of Akka developers are from Sweden, when a lot of functional programmers are in Finland. And generally, there are schools of kind of rigorous thoughts and academic departments which do this kind of work. So is there anything about geography which makes it...
I think the long, dark, and cold winters,
But why don't they spend them writing JavaScript, for instance?
Well, I mean, I don't know the precise answer to your question, I'm sure. The way these things often develop is that sometimes there's an initial group of people that sort of take hold and set maybe an academic direction for a particular university or group of universities and so on, from which sort of style like this can spring. In terms of Scandinavia, I think, and I was actually never part of this particular sort of demographic or scene, but one thing that was very popular in Scandinavia, and still is, I think, is this sort of demo scene where where people have these competitions to say, well, use the least amount of resources to do the most sort of impressive graphics demos, say, or try to subvert various games and crack them and things like that. There's a lot of interest like that, I think, in Scandinavia generally, and I think I'm not sure how that relates exactly to functional programming or to sort of more rigorous computer science, but I think that's actually a better sort of characterization of the style of work that goes on there. I think in terms of functional programming versus not, Europe actually has sort of generally had a more rigorous and more math-based or math-biased way of thinking about computational sciences.
Okay.
In fact, if you ever peruse Edward Dijkstra's archives, he has a whole set of essays about this and why two different schools of computer science are evolved in the U.S. versus Europe. And so I think that part of it is maybe more Europe versus America.
So there's a general high level of math education in Europe and kind of academic mindset?
It may not even have to do with math education, but more what the, so I think one of the things that Dijkstra points out is that, when computers first came out, so this is sort of like, right after World War II, Europe was impoverished, was getting rebuilt and so on. Nobody had any computers, and so they had to sort of theorize about them.
Okay.
Whereas in America, there was much more of an engineering tradition and discipline around these things. Computers were used for manufacturing and automation, and obviously things like rocketry, and especially around Silicon Valley, where there was a lot of defense contracting work. And so one of Dijkstra's essays sort of goes on about how maybe the reason why there's this sort of split is because in the U.S. we actually had computers that we could work with and play with, and there were sort of tangible things that we could experiment with, whereas in Europe we were left to sort of theorize about them, and so you have to sort of formulate models, and the interesting work in computer science becomes, thinking about things like the complexity of algorithms,
right.
And how logic relates to computing and things like that. And so that's one possible explanation. I'm sure. I'm sure that's not the most accurate one, but it's
a plausible one. And I mean, I can associate with this because I'm originally from Russia, which was USSR, and actually there was a similar question of lack of computers and a lot of mathematicians.
Right.
So basically people are theorizing. So a lot of, I think there was actually early crossover from, I mean, computer people had to come from somewhere. So they came from linguistics, philosophy, physics, and math. And math people theorized, and Kolmogorov and all the kind of computational complexity, and I think some data structure like AVL trees actually, I think were developed in the Soviet Union. So they thought about algorithms as a math problems. And then basically can you outline sort of your career in computers? So I know you were at Google, now you're at Twitter. Maybe you sort of can show us like what was the kind of logical evolution.
Sure. So and I've always had a sort of deep fascination with I guess how sort of anything works, but in particular computers. And that sort of very early drove me to work on things like operating systems, because at least in software it's about the lowest level you can go, and it gives you sort of a perspective on understanding the whole stack of software.
Always in terms of closeness to hardware, but there is a lot of questions and architectural
that's
issues.
Right. And so I worked a lot on an operating system called OpenBSD for a while, and I was doing a lot of work in file systems and memory management and so on. And that was a lot of fun. Now, my own progression sort of follows that of academic progression, in the sense that what we call operating systems today in academia is really distributed systems. If you go to a conference like SOSP, which is nominally about operating systems, it's really mostly distributed systems. And so I kind of follow the same trajectory and have ended up sort of working mostly on distributed systems. For the reason that sort of operating systems have kind of been, in some ways, sort of fully explored. It's maybe controversial, but and there's a lot of interesting work in a similar vein in distributed systems, right? That are happening.
This is actually an interesting view. I didn't think about this, but in fact, this is true, right? So you can actually see Finnegan as an operating system, or kind of a piece of an operating system, and now the Twitter is basically running on an operating system.
Both Finnegan and also a lot of the other things that go around it. So things like Zookeeper, things like we use a system called Mesa to do distributed scheduling. All of these things are the sort of connective tissue of a modern distributed system, and what you might consider the sort of basic services that are required to construct meaningful distributed systems. And it sort of fills the role of an operating system in the distributed environment. Now, of course, one thing that I find very interesting and I think is a sort of problem in the domain that we don't have good answers to yet is how do you sort of meaningfully write programs that are targeted to these sort of large distributed systems. Systems like Finnegan, systems like Mesos, and services like Zookeeper are sort of a partial answer to that, but they sort of assume this traditional model of programming where you write an application and issue system calls to do things like I/O. You can map memory and do things with memory and so on and so forth. But fundamentally, it's sort of the same thing, except that in a distributed setting where you have multiple of these things that talk to each other, hopefully via some disciplined approach like Finnegan. But that's not to say that's the best way to program a data center, right? And so, other sort of answers to the same questions are things like Akka, right? And the sort of actor model that largely sort of fell out of the work on Erlang. That's also very interesting. There are, there are trade-offs that you make when programming systems that way. But I don't think that we have, answers that are good enough yet, right? It's still, even if you use Akka, even if you use Finnegan, even if you use whatever else, it's still more difficult to program these systems than it should be. And it's difficult to sort of reason about the system as a whole when you're working on an individual component, right? And that has to do with everything from just the sort of mechanics of deploying these applications. If you think about how you develop an application locally, you write some code, you maybe compile it, maybe you don't, maybe you just interpret it, and you just sort of run it. You can't really do that with a distributed system, right? And so everything from sort of how you work it to how you relate sort of actions in the various parts of the systems to each other, what you consider the sort of module boundaries to be, how you distribute work, and so on, are questions that we have a lot of answers to, but I don't necessarily think those answers are good enough yet.
Yeah, it's actually more complex now, right? Because like if we look at this through this paradigm that we have an operating system in the cloud, now we still have an OS on our desktop, and basically all these issues are continuously commingled, right? Because we are using memory here, so you have to now know both stacks very well to understand what happens. But I actually like this a lot. I think it gives kind of a general view, and I've seen some things like an operating system coming from a Camel community where they talk about services and just talk this. They call it an operating system. So maybe for those who are not familiar with Mesas and Finnegan, maybe you can sort of give a brief description of what they are.
So let's start with Mesa. So Mesas is a system that allows you to sort of slice up resources in a cluster. So if you have a cluster like a data center with, say, 1,000 machines for talking purposes, what Mesas allows you to do is sort of treat this cluster as one pool of resources, and you can divvy it up any way you like. Mesas itself is sort of the very kernel of this. It's roughly like just a resource manager. So what you can build on top of Mesas, though, are things that make use of these things. And so, for example, you can imagine writing or modifying the scheduler in Hadoop to, instead of, say, install Hadoop on these 100 machines, you instead ask Mesas for resources. Like, I want a slice of resource that has 2 gigabytes of RAM, 5 gigabytes of disk, and at least 2 CPUs. And then Mesas will give that to you and sort of give you access to the machine, if you will. And so Mesas itself is sort of very low level, and sort of it's the resource manager. Now, at Twitter, we have a sophisticated scheduler that's built on top of that allows you to say, I actually want to run, n replicas of this executable, and never have more than k replicas down at any given time, and so on. And it'll sort of dynamically schedule and reschedule as it goes on. And so what it does is it sort of subsumes the part of a traditional operating system that schedules processes. Right? You can
it's
say,
like a keep alive for a process.
It does that. It does that as well. But more fundamentally, it manages the resources you have. And so instead of deploying an application to, say, 100 static machines, you instead deploy an application in sort of 100 slices. And those get scheduled dynamically throughout the cluster. And now you're giving Mesas the sort of freedom to schedule that where you can most efficiently use your resources. And so, for example, if you have an application that uses a lot of memory but not a lot of CPU, you can schedule that together with one that uses a lot of CPU but not a lot of memory, and so on. So it allows you to sort of more efficiently use the resources at your avail, but then also sort of overcomes a lot of the operational challenges with distributed systems or deploying distributed systems. For example, let's say you have static configurations where I deploy 100 replicas of my system to 100 different machines. Well, now if 5 of those machines are down for maintenance, you have to go out and 5. Maybe you have to keep some sort of on standby or whatever. Whereas with Mesas, because you have this sort of fungible resource pool, all the sort of inhabitants of those resources, everybody that uses those resources can sort of take that task together, and you don't have to individually think about it. So it removes a lot of sort of operator responsibilities from the individual sort of deploying things on the cluster. And so that's something that both allows us to use our resources much more effectively, but then sort of makes it fundamentally simpler to deploy things to the distributed system.
So you always talk in terms of CPUs, memory, and basically, so you have this actually OS level abstractions for resources. So you're not talking about in terms of nodes, like you don't say I want a VM essentially, right? You actually say I want this compute power, but you make an assumption that this compute power resides next to the disk, for instance, right?
That being said, I mean, there's what we do is we sort of delegate these resources along these dimensions, right? There's no reason you couldn't use Mesas to schedule virtual machines as well. Of course, the virtual machines would need to reserve resources along the same dimension. So it's really just this distinction is between a process and a virtual machine. It's not really a meaningful distinction, other than the kinds of trade-offs you're making operationally. Right?
Okay.
And so that's Mesas, and that certainly makes a lot of the operational aspects of distributed systems a whole lot easier to deal with. What Finagle is the following. So one way to think about Finagle is sort of the connective tissue of distributed systems. And so when you write a distributed system, you usually have a number of processes that need to communicate to each other. And Finagle does two things. One, it makes that easy to do in a robust manner, and has sort of a principled way of reasoning about and abstracting what those module boundaries are. So I can say I have a sort of a widget in Finagle that represents some logical remote service, right? And Finagle takes care of the details of like how you do load balancing and resource management, and what the application topology looks like, and so on. And then secondly, it sort of encourages or presents a concurrency model that we believe is very easy to work with, and also results in sort of robust and efficient software. And that's important in distributed systems because they tend to be highly concurrent. So if you look at a simple web server, they can handle thousands, if not tens of thousands of requests at the same time. And often it's even the case that those requests are related in some way, like maybe they share some caches. They definitely need to be multiplexed sort of onto the same connections in terms of dispatching requests and receiving responses and so forth. What we have is we have a sort of concurrency model that's based on concepts from Dataflow programming that allows you to, instead of sort of specifying, in order to compute, let's say, a search. And so, to give a little bit of background, in sort of modern search engines, you typically divide your data up into several chunks. You have to query all of them, and then sort of gather the results, and then do some processing on those results and present it. And so, the way you would do that in a traditional sort of concurrency model, like let's say using Java threads, is that you might allocate a thread for each of those requests, issue that request, use some sort of shared shared data structure to communicate the results of those requests back, and then so compute the aggregate and number respond to that query. The kind of model that Finagle encourages is a little bit different. Instead of sort of specifying the execution mechanics of doing that, you're instead just sort of specifying the relationships between the data. And so you say, well, in order to satisfy a search query, I need rather the result that is a search result is a combination of the individual results to the individual shards. And you express those relationships through what we call combinators, and you let the underlying system, Finagle, actually deal with how those things are scheduled, how the resources are shared, and so on. And when you assume that kind of programming model, a lot of the kind of synchronization concerns are sort of subsumed by the data flow itself. And so in the sort of traditional example, you have to worry about, for example, synchronizing around the shared data structure to, well, first of all, to signal when the thing is done, to actually reserve slots for each individual result and so on. Whereas if you're just sort of phrasing this problem as relationships between individual components that produce data, a lot of the kinds of concerns like synchronizations are sort of subsumed by that.
So is this what is done in future combinators in Finagle?
Right, that's right.
Actually, it's interesting. I didn't think about it as actually a data flow paradigm. I thought about it as basically like pretty simple pipelining and kind of glue, right? So that was the view which I got when looking at it, and we just did our first service in Finagle. We did a transcoding service for Verso because we use a lot of educational videos, and we accept videos from customers in various formats, and then we transcode them to the most optimal format for us. And actually, we implemented it in Finagle, and it's beautiful. It's very expressive. But for us, it was basically a simple service which interacts with Amazon Elastic Transcoder. And to me, it was very interesting to see how it works. But it's actually, I think it's a small scale. It's basically a standalone service. As we get more of them, we'll probably understand how Dataflow works better. But that's actually very interesting. So
one way to view it is that through these combinators, you can actually sort of construct arbitrary dependency graphs, right? And so in the example that I just described, it's sort of a graph that starts with the simple query, and then fans out to however many nodes there of shards you have to gather results from, and then fans in again, right? And so any sort of DAG you can really shape with these combinators.
But you still have to sort of, I mean, there is some logic which went into the design of this topology, because you know where each shard is, right?
Well, and ideally, so that's another thing that Finagle gives you, is that Finagle will, for example, in this case, give you a service per shard, and you might keep that in a sequence or whatever and map over it. But the details of dispatching those requests and so on are handled by Finagle. And this actually gives rise to another interesting sort of benefit, which is so everything that I've sort of described with respect to Dataflow, the sort of Dataflow style of programming, means that the way you sort of express the result of a query to a server, for example, is very much in a sort of declarative fashion, right? You say, well, in order to do a search, I first need to query all the shards and then combine the results in this way, and so on. And so in some ways, it's an inversion of control, right? You're not saying, make 5 queries, take the results of those, combine them together, then reply. You're sort of expressing the data dependencies. And an additional advantage of that now is that Finagle itself can take advantage of this and implement an execution strategy that is sort of optimal for that particular problem, right? So in this particular case, you might say, well, maybe we want to optimize for minimizing context switches. And because Finagle is responsible for both dispatching requests and multiplexing all the work onto several sort of I/O threads, it can, for example, guarantee that all the work that you receive in a given thread will only be handled exclusively by that thread, right? Okay. So you can do things like this, which is sort of interesting too. It's sort of analogous to having a runtime with a JIT, right? And so we haven't done much sophisticated work around this yet, but you could imagine that Finagle could, in a way, observe and profile your application and then adapt its execution strategy accordingly.
Interesting.
Which is another interesting thing that which is again future work that you might be able to do with systems like that.
It's actually interesting because we are currently looking at Elasticsearch, and I think from what you described, it would be fairly easy to do a Finagle replacement of Elasticsearch, because what it wraps a Java, and a very well-known Java application, Lucene, right? Basically, so each Elasticsearch node is a shard, basically, which is the Lucene with its index, and what Elasticsearch itself is basically the RESTful API which coordinates this, and it has obviously its own custom logic. But I think that's probably like if Finagle has the same functionality, that maybe can be an interesting hackathon project to take a bunch of Lucenes and harness them all with right. Finagle. But that brings kind of this interesting question about programming languages. So Scala, as we all know, is basically the flagship language at Twitter. I think it became known a lot because of Twitter. And what is it about Scala which made it the choice at Twitter and made things like Finagle possible? What was the route by which it took over Twitter and sort of grew with this?
Yeah, I mean, so I actually wasn't around when this happened at Twitter, but initially, Scala was used first at Twitter for a small project that was sort of orthogonal to, or could be separated out from the rest of the stack, which was written in Ruby at the time. And there were only a handful of engineers, and they sort of needed a replacement for a system they already had, which was getting pretty slow. And it turns out that Scala is a very expressive language. It took somebody just a couple of days to sort of come up with a new system that did the same thing. And because it ran in the JVM, it performed a whole lot better, just because of the quality of the runtime, basically, in this case. And that's how it sort of started. And then people saw the value of that and sort of continued using it. And there was I don't think there was any sort of conscious effort at any given point. It was sort of more serendipitous. Somebody had wanted to try for this particular project, and it turned out to work really well. Right. And then people continued using it.
But something happened, right? Because I mean, obviously, if they would have picked, basically, it's very easy to beat a long-running process in Ruby with a JVM, right? Because a garbage collector in JVM is so well tested. So basically, that could have been addressed with Java. But what happened later? It basically gave rise to all these kind of libraries, such as Finagle, and obviously there's a lot of features in Scala which make Finagle possible. So I'm just wondering, But on the other hand, there are things like Erlang, and you've written quite a bunch of OCaml, for instance, so which in many cases actually I fell back onto as well, because it's kind of a simpler language, right? So, but for instance, if we consider features in Scala, there is a lot of features, right? And some people consider it complex. Still, it was used to build a lot of systems at Twitter, and it clearly is a demonstrative case that you can have a gigantic system written in Scala and it works. So I'm just wondering, is there any intrinsic properties of Scala community or technologies which basically make it sort of suitable? So I mean, it's definitely good legacy technology Twitter now, right? So, but I'm just wondering, like, what is is it now a compounding effect that the choice of Scala and as a language which has this abstractions for concurrency and functional programming features, is it now sort of facilitating faster iterations at Twitter? Or like Twitter folks using other things. Like I'm just wondering. What's
I mean, so that's always hard to tell, right? Because you're not doing an actual controlled experiment.
Right.
I don't know if anybody's really done that to sort of set aside part of the organization, like you're going to be the control and whatever else.
Right.
So it's kind of hard to say. I think in a large system like Twitter, the kinds of things that matter for iteration speed actually usually aren't the language, right? It's basically everything else that goes around it. Everything from like the build systems to how it is to deploy things into the distributed environment. All the kinds of things that I talked about before, the sort of friction of dealing with large-scale distributed systems is sort of what I think slows iteration more than the choice of any particular language. Now that being said. I'm personally a big fan of the sort of functional approach to languages. Mostly, I think, because it sort of encourages you to write code in a way that sort of emphasizes things like value transformations over mutable data, and sort of encourages you to think in a more rigorous fashion about sort of how to exploit invariants, how to express your problems in sort of different ways that, at least personally, I feel. Leads to code that's sort of simpler and easier to reason about. Of course, this is sort of after you learn it, right? It can be quite overwhelming initially to sort of phrase problems in terms of recursion and to think of higher order functions and composition, all these different things. But once you internalize these concepts, I believe that it leads to simpler systems that are easier to understand. That's partly, I'm sure, an aesthetic preference, right? I don't think there has been a number of studies that have tried to sort of disentangle these different things and try to show that language X or this style of programming X is more efficient or effective or simpler than Y, and nobody's really had any sort of compelling results there.
Right, because I mean it's a social process, right? I mean, I think it's intrinsically related to the set of people.
That's part of it too, and there's also all sorts of different trade-offs you make, right? And so there are sort of short-term versus long-term costs, right? And so certainly, if you're hiring a sort of standard profile engineer, right? Take any engineer from a big company, even like Google. They will be more immediately productive in a more traditional imperative language like Java, if they don't have any sort of previous exposure to functional programming. And so, from an organizational point of view, once you get to be a large company, you can't only think about individual productivity anymore. You have to think about the productivity of the whole organization. And so you end up making different sort of trade-offs for that, right? And this is one of the reasons, for example, why Google is extremely strict in the kinds of languages you can use in production. It's basically Java or C++. Python is mostly for sort of operational things, I think. And that's it. And probably for Google, that is a good decision, right? And so it's just very difficult to make really sort of good non-aesthetic arguments about functional programming versus non-functional programming. It's my own experience that after you've learned the basic concepts, after you become comfortable in working in that style, that I think it's much easier to work with. I think it leads to more correct code, and I think it's also in some ways more fun. But I can't point to numbers that back that argument.
Right. I don't think it's numeric, but it's interesting. You haven't mentioned static typing, but I think it really does help in production and iteration speed if you catch a lot of errors.
Oh no, sure, but I mean that's not the exclusive domain of functional languages.
That's right. That's right. So how is at current scale? How does Twitter sort of deal with this transition of new people to functional approach? And it's very interesting, right? That you have this scale of a company. So what's your opinion, like internally, where Twitter is at, and how does it work at scale, people scale of Twitter employees at this point?
Right. And so there are a number of different things. So one is that I think even by simply using like a language like Scala, a functional language, you're kind of sending a signal to job seekers, I guess, that we're doing things slightly differently. And also the kinds of things that are, the kinds of people that are sort of attracted to that tend also to be fairly high quality engineers. And so there's a kind of selection bias going on, for one, which is beneficial, I think, for us. Again, difficult to measure, completely qualitative assessment. In terms of bringing people up to speed, we've done a couple of things. So you mentioned before that Scala is a large language, and indeed that's true. It can be quite overwhelming. So one thing we do is that we're very careful about the kinds of features you use with Scala, which is the same thing that people end up doing with things like C++. C++ is also an even larger language than Scala is. But anyway, we and this is part of why I wrote this document called Effective Scala. We sort of are careful to define the sort of subset of the language that we're comfortable with, the kinds of techniques that we consider kosher versus not, so as to make our code both uniform as well as sort of simple in construction. Right? And so basically what we're saying there is like, well, you probably get 3 or 4% better programs if you were to use things like encapsulating effects, but the sort of complexity to a programmer would rise dramatically, and so we sort of choose to, or we eschew using those kinds of techniques. And so we sort of sat down and said, well, what are the kinds of things that we believe gives you a lot of power without too much cost? And they end up being things like, well, obviously you use static typing very heavily and use the type system to your advantage, but then obviously things like first-class functions are high up there. We choose not to use mixins very heavily, for example, which is one of the things that are, at least in the early phases, was sort of touted by Scala, because it makes at least the kind of code that we tend to write more complex, and sort of prefer sort of traditional composition over using mixins as a simple example. And so that's one thing we do. And so we try to make our code look or be uniform and also simple. And then we also have a bunch of internal sort of developer boot camps, I guess, about these different things. So we have people that teach Scala from the ground up, basically.
How long does it take? So let's say you absorb a new Java programmer who's a very good Java programmer who's doing Java for 10 years, but they didn't do Scala.
You can have a person like that write Scala code in a very short amount of time, but they'll probably be writing Java in Scala.
Define short amount of
time. Like a week's time.
Okay, that's really short.
However, it takes longer to sort of indoctrinate them to the ways in which you're supposed to work or are most effectively working in these kinds of languages. And so what we do there is that, well, we do some of that obviously in the education programs that we have. But another very important component is doing a lot of code reviews, right? And so you're not gonna be say a Java developer doing Scala and then like writing your own project from scratch.
Right.
You're gonna be working with other people who are experienced, and they'll do code reviews. You'll be doing their code reviews and so on. And that way you sort of get exposed to the kinds of techniques and methods and sort of idiomatic use of the language, and that sort of seeps in, right? And then eventually you become a proficient Scala programmer.
I was going to ask basically how effective Scala is enforced. Is it kind of now a Bible? So in code reviews you can say you're violating chapter 15.5.
It's not quite that strict, but it definitely does get used for justifying certain things. Yeah.
So it can be in other words, can it be used as a operation manual for a new company? Let's say there is a Java company, and now a lot of them trying to pivot to Scala. Can they take effective Scala and make their sort of internal code review with like a core of Scala gurus, let's say, right? So can they basically say, we're going to teach people based on effective Scala, and then we're going to do code reviews, and we, will refer to basically to different things which people may violate or not follow, and can this be basically an adoption guide?
Yeah, I mean, I would do that. Sure.
Yeah, I heard, because actually I heard from some companies in the space doing this, because recently there's been a trend actually that a lot of sort of hardcore Java companies are pivoting to Scala.
Right.
Sort of in another question I had about Scala and Java, I think it stems from this famous Yammer controversy, because I think for many companies Twitter is actually in this similar position. So let's say you have a high performance process with a very tight inner loop. Right, so Yammer's choice, with the profile, then an inner loop produced by Scala was inefficient. So their answer was, gosh, we really need some, speed here. So they switched to Java, and I'm sure that the kind of situations like this might happen at Twitter processing, huge volumes of messages. So
first off, I'm sure the Yammer situation was more nuanced than that, because on the surface that sounds like an overreaction. I guess a few things. So I'm a pretty big adherent to Knuth's maxim, which is premature optimization is the root of all evil and so forth. So, however, what I like to do instead is sort of focus on having good profiling tools. And so we actually built a suite of tools that allow you to profile everything. Well, the sort of traditional dimensions you care about, which is CPU usage, lock contention, and memory allocation. And we have these profilers, and they're embedded in all of our processes. And so you can be running a service, and you can run a curl command and get a profile. So you can say, I want a 10-second CPU profile sampled at 100 hertz. Okay. And the profiles you get are compatible with Google Perf tools. I don't know if you've used these. What they do is that they use GraphVis to produce this very pretty stack call graphs for you. And usually, if you have a process that you suspect is slow, what you do to profile it is you run one of these profiles, you run it through Google Perf tools that gives you like an SVG file with a graph in it. You find the biggest box, and your answer is right there. This technique basically works 95% of the time. And so for things like this, we can expose these inner loops very, very quickly. Right? Okay. So I think the first thing to do is, well, first of all, don't prematurely optimize, and then but have good ways of profiling processes that are live in production and receiving meaningful load and so on. Now, when that happens, you can write Scala in a sort of low-level way where you, of course, have to eschew a lot of the interesting features, but you can, for example, write while loops in Scala and use mutable variables and so on. And so the kind of what we encourage is write it in the sort of simplest and cleanest, most idiomatic way first, then profile it, and then if anything comes up when you profile it, replace parts of that with sort of more performant, lower level, less idiomatic versions of the same thing, and that tends to work very well.
How often does this actually happen? Like, how often do you need to drop down to this, kind of assembly level Scala?
Yeah. So actually, in most of our systems, now I speak mostly from the sort of runtime systems perspective, the serving systems that we run, not from like say analytics and so on, where they do a lot more sort of things that are traditionally number crunching. The kinds of problems that arise most frequently actually relate to garbage collection. Okay. Right. And so, we have a lot of these very high throughput systems that receive a god awful amount of queries every second, and most of which are extremely short lived, but they're also very latency sensitive, right? And so we have systems that need to reply within a few milliseconds. Otherwise, they have an outsized effect on the total latency of the request that sort of is at the root of the query that you're satisfying. And one way to think about that is the following. So in isolation, if you have a process that undergoes minor garbage collection, let's say every 30 seconds, right? And so the sizes of heaps that we use, minor garbage collections are somewhere between 10 and 15 milliseconds. That means that every half a minute, so every 30 seconds, you're going to have, say, 10 milliseconds of pause, right?
Yes.
Which means that during those 10 milliseconds, every query will take 10 milliseconds.
So it's an unacceptable delay for these SLAs.
Well, in isolation, that's fine, right? It doesn't matter if your timeline query returns 10 milliseconds later. However, because most of our queries are very high fan out, which is to say, when you make a query to Twitter, that typically results in us needing to query in aggregate hundreds of different servers. Right? The probability that any one of those is undergoing garbage collection increases very rapidly. Okay. Right? And so if you're in garbage collection 1% of the time, right, then if you always issue 100 queries to 100 different machines, then every single query is going to encounter a garbage collection. Right. Right. And so in that way, these large fan-out systems amplify garbage collection and also other kinds of variants. So that's why garbage collection is extremely important to us, right? And that's kind of trickier because with garbage collection, you have to be very, you sort of have to, first of all, you have to know what affects garbage collection and what doesn't. Things like object lifetimes start to matter. Of course, the rate at which you allocate new objects and so on matter as well. And so we have a number of tools around that too. So we do things like allocation profiling, where you can see, where we sample allocations and you can see where your objects are allocated. But then we also have a number of, we have one tool in particular that allows us to effectively run garbage collection regression tests. And so what this tool does is, over some sort of test load, we measure how much allocation you do per request, say, and then we also measure the histogram of lifetime of that. So then we can say, well, you allocated, let's say, 10 kilobytes of memory to handle this request. Out of those 10 kilobytes, 5 kilobytes were not needed anymore, were garbage by handling 5 more requests. Right? Okay. So you measure time and the number of requests that you serve, and so that gives you effectively a histogram of longevity of allocation, and that allows you now to do effectively kind of a regression test where you say, well, I might introduce something that doesn't introduce more allocation. It can in fact reduce allocation, but maybe make some objects more long-lived. Right? And those things you can pick out quickly from this tool. So for sort of critical libraries like Finnegan, we run them through this kind of regression testing as well. Right?
Do you point back to the actual source? Which so does this profiling shows you where in your code?
No, it doesn't do that. It just gives you that would be too expensive to do in a meaningful way. It just gives you that, but if you use that with regression testing, you can compare, change by change, right? So you can say, oh, this change introduced this regression.
What does it take you then to link? Because we know that Scala does produce a lot of objects, right? So clearly, it's a tricky choice, and some things may produce much more intermediate objects than others. So I think a beginning programmer, or even an experienced programmer who doesn't normally care about this kind of stuff may not have any like intuition about this. So I'm just curious, let's say, what does it take then from you, like if you now see suddenly you're changing this histogram, so let's say you decrease the longevity of object, how do you go back to your source? How do you find, like, is it?
Well, I mean, so in this case, if you run it in a sort of regression testing environment, then you can usually point out a single change that caused the regression.
Because you know what changed in the source.
Just use Jenkins or something, and then Jenkins will either do the binary search for you or whatever.
Yes.
And so if you use it in that mode, then at least you get a sort of atomic commit that gives you the regression.
So I remember from your talk at Scala Meetup early this year, you were doing work on introducing queuing features to protocol level in Finnegan, so you can drain servers. Is it related to this kind of problem that basically would you drain a server when basically its garbage collection deteriorate because it's just it was just like living for a long time, and is this related to?
Yeah, so actually one of the things I'm experimenting with now is related to that, which is the following. So if you so one of the things I'm trying to figure out. So one of the sort of challenges with that sort of exists at the module boundaries between distributed systems. And so if you have one node in your system that's a client to another node which provides a service to that. If you sort of bring back the analogy of, well, how would this work in a sort of traditional operating system? well, that would be like a subroutine call, right? And so what you're doing now is effectively your program. You're making a subroutine call into to a library, I guess. But what you're effectively doing is that you're giving your CPU time now to that library, right?
Okay.
This does not happen in distributed systems, right? Like the resources that I have, I can't give to whoever is doing work on my behalf.
Right.
And so one of the problems that come up, and one of the things that make RPC systems challenging, is how you deal with things like priority inversion in particular. So you might have some system that has allocated a lot of resources to, but it might depend on a system that has fewer resources, so that you can't fully utilize the resources of the larger system for one. But also, that system might now be capable of sending more requests to the downstream system than it is capable of handling, right? So this is where you need things like queuing disciplines. And so queuing discipline can say, well, make sure that I only have this much outstanding work at any given time, and start reject things, only queue for this long time, or this many items, and so on. Otherwise, drop and reject work. But the way this has been traditionally done is that you sort of statically configure this. You say, this client I'm going to send at most this many outstanding queries to, or for a server you might say I'm going to handle at least this much work at a given time.
So you did the nodes essentially.
Yeah. So this is the sort of in the sort of traditional Java world. This is like how you, for example, choose to size your thread pools for handling requests, like things like that. And Finnegan allows you to adjust all those different things, right? You can say. Basically, you can sort of tune the queuing discipline. One thing that I want to do is make that more dynamic in the sense that the downstream systems, you shouldn't need to configure any of these different things. And there should be a reliable way to effectively communicate back pressure throughout the system, so that the slowest component effectively governs the rate at which you can submit work at the head, right?
I see.
Without doing any sort of tuning in between. One of the things that allows us to work on that is that we've introduced a new RPC protocol called MUX. It's also open source in Finnegan. And what MUX does is it has a separate control plane that allows you to send control messages, but it also allows you to do things like rejecting requests before they're dispatched on the server, so that a client can safely retry them elsewhere and so on, which you can't do in traditional thrift setting. But one of the things that it does is that it effectively allows you to implement a kind of flow control, just like TCP does. So a downstream server can communicate to its upstream server that I'm only able to accept this many requests, for example, or here's your window of requests at this particular time. And one way in which you can use that is you can inform your flow control by your garbage collection, right? And so you can say things like, well, let's consider the sort of bottleneck resource on my server to be the number of bytes available in my young generation. Okay. Right? And that's my primary resource. When I run out of that, I have to pause for 10 milliseconds.
Yes. Right. So that basically you can make a strategy on receiving new requests depending on
right.
your
and
internal
so then that effectively becomes your window. That's effectively the amount of capacity available in your server at a given time. And you can sort of relate that to flow control and use it to inform upstream servers. And then they can in turn use that for load balancing, for example, right? And so there's a lot of interesting opportunities here where you can effectively use this mechanism to route around garbage collection, right? Because you always have more than one replica in a distributed system, otherwise you're in trouble. And so having this kind of mechanism allows you to potentially route around garbage collections when they occur, right? And that's one possible latency sort of mitigation strategy.
That's a very interesting architecture, and surely we'll explore it. So I have endless amount of other systems questions, which I hope we can address in our future episodes. But for now, I want to ask you about the CAF conference, right? Yeah. Because you're the co-chair of this conference. I think it's a kind of storied conference. So there is a general functional programming conference, and CAF is basically the kind of pragmatic part of it, which is basically commercial users of functional programming. Right. And maybe you can tell us a little bit about this conference, about the kind of companies and talks you you'd like to see there because you're now on the organizing committee.
Sure.
I mean, I think the agenda is already set, but generally, what would make, in your view, a good conference? First of all, like, what is your interest in
Right.
organizing this? What do you want to come out of it? What kind of people would you like to meet there?
Right. So CFP is part of ICFP, which is the sort of big ACM conference on functional programming.
Mm-hmm.
And ICFP is actually most famous for its programming competition. So they have, every year they have this competition where students from all over the place sort of tackle very difficult problems in a limited amount of time and so on. The original idea behind that competition was that it was sort of to demonstrate that functional programming is superior because the teams that win will be using functional programming languages. I'm not sure they always do. I think the last couple of times have been like C++ teams that won. But regardless, so ICFP is one of probably the premier sort of conference on functional programming.
Mm-hmm.
CFP is a workshop under the aegis of ICFP and comprises two things. So there's a day of talks, and I'll get into that. And what follows is 2 days of workshops.
Mm-hmm.
And the workshops, this year we have some really excellent workshops. It's everything from sort of, we have a 2-day workshop on Haskell, like starting from not knowing anything of Haskell to being able to write, say, a web server
Mm-hmm.
that does meaningful things. We have workshops on Erlang and Scala and Clojure. And the interesting thing about these workshops is that they're often taught by the people that literally wrote the various books on these languages. So they're very high quality affairs.
Uh-huh.
Now, the talks is what I'm personally most interested in. And it's a day of talks. It's a long day of talks. And there are effectively sort of 3 kinds of talks. So one is the kind of experience reports that where people relate experience with using functional languages or functional techniques in a commercial setting. And we've had talks. We've had a lot of interesting talks historically about this. Everything from people embedding Scheme into PlayStation gaming engines,
Mm-hmm.
to people using Haskell for doing or Haskell-derived language for doing verifications for government contracts. You can imagine what that means.
Mm-hmm.
For crypto systems. To things like prototyping. One of my favorites actually was somebody from AT&T Labs or Lucent Labs now prototyping a sort of next generation antenna system in Haskell, and they did it in a week, and it just turned out to be a beautiful fit for the kind of programming you do for data processing or data signal processing, and so that's the kind of experience reports, and I find those very useful because it sort of demonstrates the applicability, for one, of functional languages, but then we hope to sort of encourage an honest assessment of how the effort actually went. And we've had some talks where they basically said, well, we tried this for a year and then we converted to Java because of these things, and they're very valuable things for the community to learn. And then there's a number of talks that are more technical in nature, so that's sort of introducing technique that are probably not of interest to the academic community, but are probably very interesting to commercial users. So that's sort of how do you in practice sort of structure large programs in Scala, say, right? Like things like that.
The other thing that would be very interesting, especially
right.
from companies like Twitter, because they obviously learn some application of functional programming at scale.
Right. So that's very useful as well. And then thirdly, we've also had a number of talks where people introduce new projects and languages and things like that are functional in nature, but are perhaps geared towards a more commercial audience, right?
Mm-hmm.
It's one of my favorite conferences to go to. There's a lot of not only are the talks really, really good, and they also tend to be very lively. People ask a lot of hard questions, and I was actually introduced to CFP by giving a talk there, and I remember giving this talk and making some claim, and then Simon Peyton-Jones immediately interrupts me and say, well, can you back this up with this and that? Right? And so it's an interesting place because we tend to get these high-profile people from the sort of academic community mesh with actual practitioners using functional programming, and hopefully, if we arrange this in the right way, they'll end up influencing each other. Right?
Yes, I see.
And so it's sort of an explicit goal of the conference to be a meeting point of the two communities, because they traditionally have been fairly far apart.
I see.
Right? So yes, and if you're all interested in functional programming, especially if you're interested in applying it in a commercial setting, you should definitely go. You don't need to have read like Benjamin Peirce's book to attend this thing. It
helps, but it's not necessary.
Right. It's meant to be it's meant to be sort of comprehensible to anybody that is a programmer, basically.
So, I think ICFP and GAF are fairly traditional conferences by now, but recently we've seen some new entrants such as Strange Loop, and this year actually Strange Loops is a few days before the GAF, and maybe, I see this sort of mix of academic and industry community, a distinguishing point in GAF. Are you aware of any kind of other stylistic differences? Because like Strange Loop, I think it's similar in agenda in terms of closure, Haskell, Scala,
right?
And what would be your take on sort of?
Well, I mean, CFP is a more sort of focused conference, right? The sort of explicit goal is, well, as the title says, commercial use of functional programming, which whereas I believe things like Strange Loop are more sort of general technology trend conferences, right?
Okay.
And so it's much more focused, right?
Okay.
That being said, I've never been to Strange Loop, but it always looks excellent to me.
Yes. So hopefully all of you guys who are watching this can make this CAF this year, and we thank Marius for coming, and hopefully we'll cover much more topics in our future episodes.
Sounds great. Thank you.
That's it.
All right.
Good job.